I'm Wendy. I work at CFAS in the UK. I'm going to talk through the work I've done on trying to see if we can incorporate machine learning in our site choice modelling for recreational fisheries. Yeah, so for some background, so I'm sure you all know, marine recreational fishing is a high participation activity in the UK with significant social and economic benefits, and it can highly impact fish stocks. And to manage it effectively, we need to be able to understand anglers' preferences and behaviours and how anglers will respond to changing conditions. And one way that we do this is through site choice modelling. So we look at anglers' revealed preferences through the sites that they choose to go to fish. And this is normally done through standard or parametric discrete choice models. So these are really good at being interpretable, and they can naturally link to welfare and willingness to pay measures, but they also impose quite a lot of strict assumptions. So you have to pre-specify the functional forms and any interactions, and they can be kind of difficult to do when data is a bit more messy and complicated. And since site choice often depends on a lot of different factors, so distance and past visits and catch expectations, the effects can often be non-linear and interacting. And machine learning can often capture non-linearities and interactions flexibly directly from the data without you having to pre-specify anything. But they're often criticised as being a bit of a black box, so it's hard to then get any interpretable things out of it. So we wanted to explore whether we could use a tree-based machine learning model in XGBoost to see if we can improve our predictions of site choice modelling and see if we can get reasonable behaviour interpretations out of it. So to do this, we used our sea angling diary data. So it's a online panel where anglers sign up to report their catches and their fishing activity, and it's been running since 2016. Age, gender, regions, and then we can also get their fishing trips and fishing activity, so we can get where they go, how often they go, and what they normally catch. And you can see from the plot we've got quite a good wide distribution. These are jittered, so they're not exact, but they give you an idea of the range of where the anglers are and what their sites are, generally. And then from that information we can calculate the distance that they travel to get to their sites. And then we also calculated a habit variable based on the number of times they'd been to a site previously. And then from their site locations, we're able to get a range of characteristics. So we've got things about the substrate, depth, tide, weather, and then a range of amenities that are available at the site. So we used a distance as a proxy for that. So distance to parking and roads for accessibility, and then to cafes and restaurants for things available at the site. And then we also needed to create a choice set. So for every time they fish, they make a decision about which site they're going to choose. So we had to create a list of alternatives that they were choosing between. So we used all of the sites that they had previously visited for each choice set. So then they can decide based on that. And then we also created an expected catch variable based on what had been caught at each site previously. And then once we had the data sorted, we then split it into a training and validation set. And then we used two types of models. So we used the extreme gradient boosting, the XGBoost, which is a decision tree based model. So it runs decision trees sequentially and can learn from previous errors. And then we trained that as a logistic classifier, so you get a score for each site within a choice, and then we applied a softmax normalization to get a choice set probability. And then we weighted each trip equally, so choice sets with more alternatives don't influence it more than ones with less alternatives. And then we tuned the hyperparameters to optimize prediction and avoid overfitting. And then we compared that. Oh, and then we can get the interpretation using Shapley additive explanations, which effectively give a value to a feature contribution and can tell you the direction of how it's influencing the predictions. And then we compared that against previous work that we'd done using more standard-based approaches. So we'd fit logistic regressions to model site choice in the past, and we did it for region and avidity and an overall one. And then we compared the two with compared the predictive performance of the two types on held out trips. Overall, so this is an overview of the data. So the anglers we included, we had 1,295 diarists across over 30,000 fishing trips and 1,174 different sites across England and Wales. And the number of alternatives ranged quite a bit, but it averaged at 12 sites per angler, and that's a plot of how it ranged throughout the diarists. I think that's supposed to be it averaged at 2.6. Oh no, average of 26 fishing sessions per diarist, but again that ranged from 2 to 636. So we had quite a lot of difference in our diarists. And then the site use also varied by diarist as well. So one angler visited the same site over 500 times. And one angler visited 51 different sites across 150 trips. And anglers generally revisited a site an average of 5 times. And again, the distance travelled varied. So that's this plot down here. So it varied quite a bit by region and by avidity levels. But it averaged at 52 kilometres per angler. And again, it ranged quite a lot. So from almost nothing to 575 kilometres for one trip. This is the results of the model comparisons. So we compared the predictive performance of the GLMs and the XG boost on held out sessions, and we computed metrics. We did session-based metrics. So top one is like the hit rate. So it's how often the actual chosen site was ranked top in the choice set, and the AUC, which is the ranking performance. So it's how often the chosen site was ranked higher than the non-alternatives or the non-chosen alternatives. And all of our models outperformed the random baseline, which for the top one was 0.15, so they all outperformed that. And the XG boost outperformed the GLMs quite significantly, so the hit rate of the XG boosts was 0.45, so 45% of the time it got the answer exact, and the GLMs was only 25% of the time. And then we also ran a bit of a feature sensitivity analysis. So what happens when you take the key explanatory features out of the XG boost and run distance only, habit only, and then one without habit. So you can see the distance only was the worst performing one, but it still was roughly the same as the GLM. and but when you use only a habit variable, you get most of the you get it right most of the, oh, it's most similar to the full set. But when you take habit out as well, it's still able to compensate for that lack of information with the other variables that are available within it. So I think it's quite a good model, I guess. Reasonable. So this is the explanatory bit. So the shapely additive explanations that gives you like a feature importance. So this is a magnitude only thing. So it tells you how important characteristics were to the model, and we grouped them into smaller categories so it's easier to read. And overall, the angular characteristics was the most important. So things like the avidity, region, and age, that accounted for 25% of the importance. And then what people expected to catch, like the different species that they wanted to catch, when you combine it all together, it was also the next important. And then habit was also quite significant. And then the travel and amenities that were available at the site were more secondary to the key features. And then this gives you more of the direction as well. So this is the SHAP on a log odds scale. So I'll have to try and remember how to explain it. Yeah, so it gives, this is all the characteristics, or this is all the features split as they go into the model, and then it gives you how each variable impacts on the model, and then it's listed by the feature importance. So the ones more at the top had a bigger influence on the model than the ones down at the bottom. So the top three features overall were avidity, previous sites, and travel distance. And then it also gives you the direction in which it affects it. So the ones, as it's more on the right-hand side of the plot, it tells you that it increases it increased the model's ability, or the model's likelihood of choosing that site. And then the colours also tell you the feature value. So for travel distance, because it's all blue on this side, when the sites were closer, it increases the model's prediction of that site being chosen. And then it's like the opposite with previous visits. So when they visited a site more often, it increased the model's likelihood of choosing that site. Yeah, I hope that makes sense. So yeah, the key contributors were the previous visitors that had a strong positive contribution, and then travel distance, the strong negative, which is kind of what you expect from this sort of thing. So they kept returning to the same sites, and they liked sites that were closer. And then there was major differences in the region and avidity groups, but the other variables were more secondary. So this gives species individually instead of grouped. So it tells you which ones influenced more. So they tended to prefer sites with cod than sites with whiting, and they tended to avoid sites that they had in the past not caught anything. And then you can also split it by different avidity groups, and it gives so overall the top three was still the same, so avidity, previous sites, and travel distance and region, and then it changes the different species that were important to different groups of anglers, and different amenities that were important to different groups of anglers. I think I'm running out of time, so I won't explain that too much. So yeah, overall, the XGBoost improved our site prediction model, and habit and distance was still strongest, so that's what we kind of expect with this sort of thing. But it doesn't, it supports interpretation, but you can't get welfare and willingness to pay type things out of it. So in the future, we want to try a few different types of models, which are a bit more hybrid types. So they combine machine learning and then with the structure of the random utility models, which you should hopefully then be able to get a willingness to pay for different sites out of it. So that's quite quick, sorry.